Good afternoon, ladies and gentlemen. Welcome to TechGig webinar series, our endeavor to empower techies. We believe that sharing of knowledge is the key to enhance our skills and grow us as professionals. With this principle in mind, we have initiated a series of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is Software and Electronics Engineering, Process and Progress in Innovation. Our guest speaker today is Mr. Dave Ranson, Managing Director at Moog India Technology Center. Mr. Dave Ranson began his aerospace industry career in 1981 with Moog Inc. In the ensuing 30-plus years, he has been responsible for developing leading-edge technology for several major aircraft programs. 15 of those years, he has worked as a senior manager leading the design, development, and qualification of flight-critical aircraft components with responsibilities spanning the US, UK, Brazil, and India. Dave is a professional mechanical engineer registered in the state of California. His education includes a Bachelor of Science degree in Mechanical Engineering from the University of Southern California, an MS in Mechanical Engineering from the State University of New York at Buffalo, and a President MBA degree from Pepperdine University. As Managing Director of the Moog India Technology Center, Dave has guided the development of critical engineering competencies in a qualification test laboratory as well as achieving AS9100 certification. Current projects include embedded flight control software and electronics, flight control actuation components, and qualification testing for the Boeing 787 and Airbus A350. Moog's India Technology Center is now a center of innovation for key technologies that support aerospace, automotive, and industrial controls. So without further delay, I introduce you all to our guest speaker. Over to you, Mr. Ranson.
Good afternoon. I've been looking forward to our talk this afternoon and to hearing from you. Let me just show my title slide here so you can all see it. So today we'll be talking about electronics and aerospace. I want to make this time valuable for you. So while we give you a brief look at aerospace as an industry and as a possible career, I encourage you to think of questions that you might ask at the end. Today we're going to focus on electronics and aerospace, but before we start, I have a very important question for you. Both engineers who are in school and engineers who have started their career. Why did you choose engineering instead of another profession? As we're talking, I'd like to have you consider that, and we'll come back to that later. Just slides may take a little delay here to change slides because of the internet. Sorry about that. While we're talking today, we'll be covering electronics and careers in aerospace as well as the topic of electronics. To get us started, I'd like to give you a context for our discussion. I'm, of course, with Moog right now. I've been in business for over 30 years. I've been with 4 different aerospace companies, each of them very good in my career. And it's given me some additional perspective on the industry. Just to tell you a little bit about Moog so you understand my perspective, Moog is a worldwide designer, manufacturer, and integrator of precision motion controls. We're in 28 countries, and we're over 11,000 people. Our annual revenue was $2.3 billion last year, and this year we'll close at about $2.4. Moog's innovative technology solutions are found literally everywhere, from military aircraft to space vehicles, and even to the retractable roof at Wimbledon. Aerospace brings together key engineering disciplines to develop complex systems that meet the extreme demands of aerospace. In particular, we want to focus on the fact that aerospace systems demand a systems engineering approach. And on the screen you can see little symbols that I've shown to indicate the different domains. Control theory, mechanical engineering, electrical engineering, which will be our focus today, computer engineering, and then an overall systems engineering function that helps to define common requirements and processes and to validate and verify the systems that we design. I'd like to have you think about that question I asked you earlier. Why did you choose engineering? And then I'd like to take it a step further, because I think this might help you answer another question. Why choose aerospace? Keeping in mind that aerospace is not for everyone. I'll tell you why I chose aerospace as my career. Number one, I love the fact that we design, build, and test things that fly. And there's nothing better than that. You can see some of the vehicles there. I've worked on several of the planes in this picture, actually. Another reason, though, is in aerospace, we design vehicles that can go anywhere, even to Mars. On the other hand, getting into aerospace is not easy. It takes hard work, and you have to be good with math and science. And hiring is very selective. But even though it's hard work, it's worth it, because we get to work with the latest technologies. In some cases, we're asked to invent new technology, and once in a while, we get to be part of making history, like the historic accomplishment of the LCA, the Light Combat Aircraft, which has been developed here in India. There is another side of this business that we must never forget. Millions of people fly on aircraft every day, and they depend on us. They've come to trust that the aircraft will indeed make it to the intended destination without any problems. Let's talk briefly about the serious side of this business. Now, the reason I showed you that very sobering slide was as a reminder that aerospace is also a very serious business. This was an actual passenger flight that crashed during the landing in Amsterdam Schiphol Airport. 9 people perished. The initial investigation showed that this was due to a system malfunction in the flight control system. There was a faulty radio altimeter that gave a wrong signal to the flight control system. And the auto throttle, which is something that's designed to act without the pilots having to control it, decreased the engine power, but the crew noticed it too late to take appropriate action. This is serious business. In aerospace, lives are at stake. We take every precaution to make sure that our products are as safe as possible, because 90% right is not good enough. That's why the engineers are so important in this business. It's our job to design, build, and test products that are safe. At the same time, provide the highest performance, the lightest weight, and the best manufacturing and cost performance. Okay, let's talk about what you might do for electronics in aerospace. Talk about some of the challenges and opportunities. If I could start with this basic control schematic. If you're in engineering school, you've seen this kind of a block diagram before, showing a simple feedback control loop. This is at the top level, very, very simplified, where you're showing feedback compensation around the entire aircraft system. In fact, there are many, many control systems controlling an aircraft. Early on in, I'm sorry, let's see if I can go back. Well, that's okay. So the progression of aircraft control systems over the last 70, 80 years has gone from pure mechanical controls with cables and pulleys to, in the 70s, with large aircraft, hydraulically assisted, and then finally completely hydraulic controlled control systems. And these were, there was always a connection between the pilot's control and the surface, and usually redundant, meaning if one system failed, there was a backup to support it. Let me just show you a little video about that, just kind of a good illustration. This talks about just that migration from the early mechanical controls to now an autopilot. You can see that moving in the pilot's cockpit there, and then a dramatization showing how the autopilot was developed to take some of the workload from the pilot. You can see the mechanism there. And then they'll illustrate the fact that with these mechanical controls, levers and pulleys and cables, with hydraulic assist, the next logical step was to replace those cables and pulleys with wires. And you can see, as this shows now, a great simplification in the aircraft's complexity, which meant less things to go wrong. After that, the natural thing to do was to make the pilot's control simpler using just electrical signals. So that was basically that got us to fly-by-wire. So we'll go to the next one now. All right, so today, in modern aircraft, I'm going to show you here, this is the Grumman X-29, which is the 25 years ago an experimental aircraft. And you can see that the flight control system diagram shown here has quite a bit of electronics in it. You can see the backup sensors, you can see primary sensors. Over here you can see in the different control axes LVDTs, which are sensors that tell the position of the surface. Here you can see that for the X-29, they were just using digital control systems in experimental manner. They also had a backup electrical control system that was all analog. Today's aircraft don't require these analog backups. And then you can see here the different flight control surfaces. So this is, we've just taken it from purely mechanical now to completely fly-by-wire aircraft, where if the electrical system fails, there better be a backup because there is no connection from the pilot's control stick to the surface. Let's just talk about, going back to the accident, let's talk about how do we design systems. There's always a trade-off between how heavy an aircraft is, because if you made something very redundant, meaning there were multiple systems to backup systems, eventually an aircraft would be so heavy it wouldn't fly. And so there's always a trade-off. And these kind of trades are done not just in aircraft systems, but also in automobile systems and rail systems, where on the left-hand side of this axis you can see the consequences of a failure. Anywhere from at the top of this, where it's the catastrophic accident, where lives are lost, and then getting less and less severe, going down. An adverse effect on the occupants, maybe somebody would be injured in this case. Here is just aircraft damage, and then all the way down to just nuisance failures. In this axis is the probability of a failure. If it's very likely that this failure could happen, then this graph gives us a clear picture that it had better be just minor things that happen if it's the probability is likely. Improbable means something like 1 in 10 to the 6th, 1 in a million chance of a failure that would result in airplane damage. And if you use this simple model that's shown here, extremely improbable failures might be something like 1 in 10 to the 9th. So that gives you an idea of the kind of engineering decisions that have to be made and the calculations that have to be made in designing a flight control system. This next picture talks specifically about what we do with that information. Basically, understanding what the probability of failures happens in a very disciplined manner these days per this procedure, ARP 4761, safety assessment. And then we design systems in a parallel process, 4754, to meet those safety requirements. And these, the criticality levels we talked about just in the previous slide, are dealt with between the two procedures. Now, today we're going to be talking primarily about electronics, the hardware side, but there's also a parallel software side which has the same kind of rigor. We'll be talking about software in a few weeks now. Software is controlled by a process that's very rigorous called DO-178, and that defines a specific process. And the thought here is that software can never be 100% inspected. You can't find everything that could go wrong, but you have to be able to prove that you have a process that you follow and you never deviate. And the process over time is proven to be very robust and to prevent failure. So that DO-178 is the Bible we use for software design for aircraft. There's parallel specification requirement for electronics hardware called DO-254, which again requires the same kind of rigor in the process we use to design. And because some of the functions cannot be completely physically inspected. I'll just speak briefly about DO-254. We won't spend a whole lot of time on this. Today, integrated circuits are part of our lives. Most of the appliances in people's homes have integrated circuits, but in the aerospace, the circuits can be very complex and very difficult to test. Some of them, the ASICs that are referred to here, are application-specific integrated circuits, very specialized and require very special testing to prove that they won't fail. So ultimately, DO-254 has provided us now with the design assurance guidelines for airborne electronic hardware. This table shows in words what we talked about in that table earlier. Catastrophic, meaning level A design assurance is required, and that's for probability of 10 to the minus 9th. We won't spend a lot of time on this table. So design assurance in general, how do we go about that for electronics? There's a very structured way of designing, and it starts with having plans for how we're going to manage that, having standards that we use for our process, and then having requirements documents right up front from the aircraft level or from the spacecraft level. From there, the schematics are formed, test cases are formed, and after the designs are done, there's a rigorous testing process for verification, validation to make sure we really have accomplished the requirements that were set out up front. Very important for all of this is documentation, both for quality assurance and for configuration management. You need to know that you built it correctly, and you need to know that you built it according to specific requirements. In all of these cases, when it flies, the Federal Aviation Administration requires that these tests are witnessed and documented very carefully. I'll just mention this too, although we won't spend a lot of time on it today. Electronics in aerospace has to do not just with control systems, but also with monitoring and reporting. And this is an indication of the complexity, but it's an interesting turn I should mention to you. On the left is the cockpit of the 747 in the early 70s. And you can see there's a significant amount of electronic hardware in the front, on the top picture on the top left, and then bottom, that's the same cockpit, but the rear view. Now, if you look at the same airplane, almost 20 years later, the 747-400 is much less complicated. And the idea is it's to make it less complex for the pilot to fly, meaning less errors and less fatigue. But the price is fewer controls for the pilot to manipulate, mean that those controls are more sophisticated. So the electronics behind those are all more complicated. The disciplines that you'll encounter in an aerospace company like Moog or some of our competitors, you would find several of these disciplines. Analog electronics. We still use analog electronics for key applications. There's a lot of digital electronics, more and more in our product, but there will always be some of both with you. You also need to be familiar with hardware description language called VHDL, and it'd be good to have some microprocessor knowledge. Now, we don't expect that a student coming in would know the specific microprocessors that we're using today. And even if you did, those would become obsolete, and in a year you'd be needing to learn about a new microprocessor. What we expect you to be is willing to learn and to have a basic understanding of microprocessors based on your schooling and your experience. Power electronics is a major area in aerospace these days, where 20 years ago most of the high power applications were provided by hydraulic power. Today, more and more we're finding what is called the more electric applications. So power electronics, significant power levels are prevalent in commercial aircraft and military and space. Another thing that would be helpful is to know about data buses. Some of these would be familiar. You probably recognize RS-232 and certainly the Ethernet. But there are some specific aircraft-related buses like ARINC 429, one of a series of ARINC data bus protocols. Middle standard 1553 is used commonly, both military and non-military jobs. So those are all basic disciplines you might find as an electronics engineer, and you would probably specialize in one or two of those in your career. We would certainly not expect you to be an expert on all of them coming in, and in fact, very few people become really proficient at all of those. I will go through these fairly quickly because I think it's perhaps just the names will give pause for a question at the end instead of listening to me read all the text. So component selection is an important part of designing electronics. Time margin analysis, understanding that the logic functions on your circuit board in fact all play together, even in extreme cases. Power dissipation analysis, very important. Power is both a problem for heat and a problem for fuel consumption for an aircraft or a spacecraft. Thermal analysis, for obvious reasons. Vibration analysis should be coming up there. Packaging challenges. Another very interesting discipline. Packaging pulls together multiple disciplines: thermal, mechanical, magnetic, electrical. The person who does packaging ends up having to understand and deal with the challenges of packaging and meeting all those conflicting requirements. EMI, electromagnetic interference, is a major challenge because the electric field's set up not just by the components in the aircraft, but also in the environment that the aircraft flies through is important. And then the flip side is electromagnetic compatibility, meaning radiation. We don't want the aircraft to be giving off so much electromagnetic signal that it's a problem in the neighborhoods that it flies through. Some other things: functional testing, high and low temperature testing, vibration and shock testing, and then test data analysis, and then if something went wrong, failure analysis. Those can be very interesting challenges, and an electronics engineer has many places where he can engage. We'll just look briefly at the workflow of electronics design. Initially, we have to understand the requirements and map out an initial design using a block diagram. From there, the drawings of a schematic are started, and simulations are often run at this point before we commit a lot of effort to specific design. That's one wonderful thing about today is we have some wonderful simulation tools that allow us to understand potential problems well before we've committed a lot of time or money to a specific design. Testing at the card level is the next step after understanding you have a good theoretical design. And ultimately, based on successful card testing, you would integrate that and test at the controller or the box level is what we call it. Each one of these, as a new engineer in this process, at each one of these stages, you would have a subject matter expert as a resource to help you review your work perhaps, and then as you got better at it, to consult with. And each step of this, part of our process is peer review, where we help each other by reviewing each other's work to make sure there isn't that one mistake that we forgot just because we overlooked it. Designing for critical applications is really more, it's using that same process, only there are specific interim steps we take and just additional care that we take because ultimately, as we said earlier, this is a serious business. So we use, we're very careful in layout to make sure that spacing between traces on boards will meet thermal and electrical challenges. Vibration is always a concern. And we have quite a few tools that we use. You can see at the bottom of this slide, Allegro, OrCAD, AutoCAD, Unigraphics, the list goes on. Another benefit of today. I'll just show you real quick. These are a couple little R&D jobs we did. The one on the left is a resistor failure. What happens if you put too much current into a resistor? And what would this look like on an airplane? Not a good situation. So we're looking at what possible solutions you could have. Now you're going to see in this one there's a failure also, but you'll notice that it's not nearly as spectacular, actually kind of boring, because we're trying to contain the fire hazard. Should be just about now. There you go. You can see it. There's a failure, no fire. So things like that can be kind of fun. We do R&D. Part of aerospace is R&D, and that's fun. So career paths. Let's just talk a little bit about that. In aerospace, you can enjoy great career success, and you can make a good living without becoming a senior manager. And I think that's important. In some companies, like Moog and in the aerospace business, the technical career path is valued just as highly as the managerial path. Specifically here at Moog, the designation principal engineer is respected and compensated as highly as an engineering section head would be. The message is you can be very successful as a techie. Now, the reason that works, especially at Moog, is because of our values. It's not about titles or position. It's about the job you do. One of our values is competence is king, and what that means essentially is a fresh engineering graduate or an experienced engineering manager all gain respect for being good at what they do. So competence is king. That means that on a technical path, you have a chance for real success. But it also means you're going to need to have a deep knowledge of the products. And it means you'll be expected as a senior person to have sound engineering judgment. And you know the joke, don't you? Good judgment comes from experience. Experience comes from making mistakes. That's what this is about here. Sound engineering judgment, the kind of judgment that's needed for flight critical systems, comes from experience. And that's the other part about being in aerospace, is having your seniors who have lots of experience walking with you to help you learn. Aerospace products are some of the most sophisticated, complex products in the world. The design, development, and certification process usually takes at least 3 years, and it's often 5 years. It can take years to gain the deep product knowledge that I just talked about. Career paths for true aerospace companies look much different than in engineering services companies, and I should point out that is good for you. In engineering services companies, you can see rapid advancement and perhaps a title in some places with an early career salary benefit. However, in some companies, you have to be aware that sometimes the opportunity to advance may be limited because so many people compete for the top spots. You need to decide what's important to you and then decide if aerospace is for you. Aerospace careers are more slow and steady. They provide solid, steady growth in salary and a good salary. They provide the freedom to learn and to grow deep in your domain, to get that deep experience about products and the solid engineering judgment that you'll need as a senior. In an aerospace company like Moog, you have more opportunities. And this is very interesting. In aerospace, you have the opportunity to build long-term relationships with global experts. You have a chance to build a reputation for yourself in the international aerospace community. And that can be very gratifying. Instead of being one of thousands on thousands, you can end up being one of a very small community. The key word in aerospace is patience. So what qualities do aerospace companies look for in engineering candidates? Number one, we're looking for someone who's eager to learn. We're looking for someone who's prepared to make learning a priority from day one, to look for assignments that will provide learning and growth, to be willing to be coached and mentored, and to look for someone to help them learn as fast and as much as possible. The first few years of your career can literally shape the learning curve of your career and possibly your life. Learning is an important part of living. We're looking for self-motivated people, candidates who don't just wait to be told what to do next. Right alongside that initiative, we look for someone who's volunteered for activities that allow you to show that you have you acquired important skills, both soft skills, the people skills, and hard skills, the technical skills. So we'll be looking at a fresher. We'll be looking for someone who's taken the opportunity to demonstrate that in their either in their school or in their community. Very important is the last one in this slide, passion. I should say that again more passionately. We are looking for someone with passion, someone who has enthusiasm and commitment to work hard in pursuit of a worthy goal. So what else do we look for? We look for leadership. We look for someone who has demonstrated the ability to plan and organize and to energize a group to action. Maybe you've organized an event for a large group of people. Maybe it's even a company party or something that requires negotiation, motivation, and flexibility. There are lots of opportunities for that if you look for them. We're looking for someone who can inspire others. It could be as simple as convincing a group of your colleagues to undertake an activity or maybe to set higher goals. And then maybe one of the most important is communication. This is perhaps the most neglected skill, even by experienced engineers. A professional writing style is a key resource, a key accomplishment for you all during your career, and I would encourage you work on it now. And then, of course, verbal communication, definitely critical to the success in an aerospace firm, because aerospace is a global business, and if you're in aerospace, it's very tough to get through a year, maybe even a month, without talking to someone from another continent. Leadership development is very important to us. We just talked about leadership as something we're looking for in you. However, we also recognize that once you're here, there's more leadership development necessary to help you in your career, both to help you succeed and to help the company survive. At Moog, it's fairly simple when you think of what we're really looking for folks who are going to go to the next level to be more of a leader. Number one, and not optional, this is absolutely required, is you have to be technically competent in your domain. You have to be a good electrical engineer. Whether your domain is magnetic analysis or power electronics design or component selection and obsolescence, you have to be good at what you do. Then, and only then, do we start thinking of you as potentially a leader, and then we look for these others. We look for initiative and ownership. We talked about that earlier in every employee. We look for someone who can get things done through others. And what that means is a combination of being able to plan and organize, certainly, being able to delegate, certainly, but it also means being able to work with people to help them succeed, to be able to look out for the group, the good of the team, before yourself. And then the third one there is building relationships at all levels. Our expectation is that an engineer in an aerospace company will need to work with their peers very well, build relationships, because relationships are the glue that hold things together when there are difficult times. We also expect that an aerospace engineer in electronics or software or mechanical will be able to build relationships, meaningful relationships as colleagues with their seniors, and be able to talk with confidence and communicate clearly with executives, perhaps several levels above them, as well as to be able to talk with those who are perhaps reporting to them. So, what should you do to prepare for an aerospace career in electronics? Sorry, the typo, in electronics. But the advice is the same no matter what. We want you to learn one thing well. Master the foundations of your engineering domain. If you really understand the why of things, the physics, and you have some solid math skills, you'll do well. What does that look like for aerospace electrical engineers? Excuse me. We recommend you have a solid understanding of your core subjects, and that means primarily electrical, but some computer engineering, and maybe a mechanical heat transfer course. Exposure to systems engineering concepts is a plus, and practical experience in a test lab is very helpful. Things you should know are how to deal with algorithms, C programming language, perhaps Ada. It's not used in many programs anymore. Understanding real-time behavior, digital electronics and processors, FPGAs, also non-volatile RAM programming, memory addressing, and digital bus protocols like we talked about in 1553. Now, we don't expect you to come knowing all of those things, but we would like you to be able to understand how algorithms work and perhaps how to use C programming and maybe how to do some low-level programming. But what you don't know, we can help you with. So there's one other thing I'd like to talk about. Aerospace companies look for an understanding of how parts are manufactured and how they're assembled and tested, not just how they're designed. Without that, it's common for a young engineer to propose a solution that's either impractical, that you can't build or test easily, or costly because it has expensive materials or processing in it. The way to understand, to really get to understand that, is to get your hands dirty. And by that I mean the best kept secret of all is get out in the lab. Take training in manufacturing for how microprocessor boards are built and how they're tested. Work out in the shop and the lab to understand the challenges that are faced in the lab. That is a great benefit for you, and probably is one of the best kept secrets in the business. So the most important thing, employers are looking for more than academics. We're looking for problem solvers, not test takers. The problems that we have to solve require a fresh perspective, not a textbook answer. So the most important thing for your career is to stay curious. The most successful mechanical engineers and electrical engineers are those who want to understand the why of the question, not just how. So as we wrap things up here, if I can just pull that back together to say that electrical engineering for aerospace is challenging and it's exciting, but it's also serious business because, as we said, lives are at stake. As you prepare for a career in aerospace, learn one thing well. Master the foundations of your discipline, whether that's electrical engineering or computer science. And stay curious. Never stop learning. Never stop wondering why. So, with that, I'll hand it back over to the moderator. I'll be glad to answer some questions. And if you want to follow me on Twitter, my address is there.
Well, thanks for the insightful presentation, Mr. Anson. Let's quickly take up the questions now. I have assigned you some of the questions. Please read out the questions and the answers from the questions pane so that our users may listen to your commendable insights.
Okay. The first one I see is from Sadhguru Prasad Gaur. In the diagnostics, I'll read his question. It sounds like a good one here. In the diagnostics, it's understood by my experience that if we are able to bring the fault back, then we have killed the problem forever. How do we use this technique in aircraft fault diagnosis in keeping history of fault analysis? Okay, I'm going to repeat what I think your question is. I think what you're saying is that to understand if you really have fixed a problem in a circuit, you have to be able to repeat the behavior that you saw that caused the failure. And if you can't repeat that behavior, see the failure again, and then show that you've stopped that, then you don't really know for sure that you've solved the problem. I think that's what you're saying. And so we use that same logic in fault diagnosis on aircraft. However, it's also aided by sophisticated test equipment that can often do a lot of that checking for us. And we don't have to go down to the individual component level to do that. Next question is from Rangarajan. Sorry. How can one control the shift in the function of the control system? Excuse me. Will it be in context to decimation in time domain or frequency domain? That's a very specific question, and I'm gonna I'll tell you what. Why don't you send a note to my my Twitter or my website, and we can talk about that one later. But I think we need to talk about a little bit more specific there before we can make a general comment on that. Next one. Does the recession in the IT sector also affect the electronics sector? Let's see. I would say there's more than one question there, really. Right now we're seeing a recession in the IT sector, which is driven in part by some of the economic challenges that we see in Europe and the U.S. and that looks like it will continue for a while. The electronics sector for aerospace is a little less sensitive to that because it's driven by the needs of the aircraft industry. Many of those needs are driven by contracts that are already in place and are less susceptible to short-term downturns in the industry. But if the recession were to continue for a long period of time, it would eventually affect the electronics sector for aerospace. I'm not going to comment on consumer electronics. Okay, let me just make sure I've got my screen here for questions going. So the next question is coming up. I'd like you to think about the question I asked you earlier about your career. Why did you choose engineering? If you chose engineering because it's a respected occupation, bravo. I chose it for that reason too. If you chose engineering in addition because your goals are to be very financially successful and to have a very important title, aerospace can also provide that, but it won't provide it necessarily as quickly as an engineering services career would. However, long term, if your goal is to be involved in an international community, a global fraternity that's solving technical problems, then aerospace is a very good choice for you. Let me just answer this next question here. This is from Kiran Kumar. Completed my BTech in Electronics and Communication in 2012. Congratulations. Interested in automation domain. How can I apply for that? At present, I have experience on the 8051 microcontrollers only. Can I meet the needs to enter aerospace? I've had a little experience by developing a prototype for solving a problem of a farmer. Ah, good for you. Practical experience is one of the best teachers. Let's go back to your other question, though. Right now, your question is, number one, how to apply for or begin working in the automation domain. And I think the second one is, does your 8051 microcontroller experience, is that applicable for aerospace? For the automation domain, I'm going to have to defer to the standard answer there. There are today more and more applications for automation. We do automated assembly and test, and of course our manufacturing is very automated. But any industry, just about, is seeing some level of automation, and so I don't think there's a specific difference for aerospace that I would offer for automation. For the experience with the microcontroller, our desire is that you have an understanding of how to deal with the performance and perhaps the design of electronic components. And the 8051 experience could be very helpful for you in just understanding, in general, the behavior of a microcontroller product. So I would say it would not disqualify you, and having some experience with a microcontroller is better than having none. So do we have another question? Let's see. Well, we're waiting for the next one to come up. I'll just mention that we're going to be talking about software coming up. That's planned for next week. And then in October, we're going to talk about mechatronics. Some of you, if you're electronics engineers, will find that mechatronics would also be a place where you can find some real good challenges. So how about that next question?
Well, that is
So
all
did I
we...
start it off with our picture of flight?
Yeah.
You go ahead, that's fine.
Yeah, well, that is all, Mr. Anson, we have from our users for the queries. Thank you so
Great.
much for your session
Okay.
on software and electronics engineering, process and progress and innovation. It was indeed a great
Thank
session.
you.
I would also like to thank all our participants for the support in making this webinar a success. The recording of the webinar will be available on techgeek.com by evening. Thank you all. Have a great evening.
Thank you. So, looks like we had 41.